We're talking about chapter 13, and what we're talking about is displacement efficiency in one dimension. Okay, and so you can think of it as being this rock core where we inject water, so 100% water, fractional flow is equal to 1. It pushes oil out, so on the other side we produce oil. And early on, maybe it's all oil. You put in water, you produce oil. You put in more water, you produce more oil. That's ideal, right? Water is inexpensive. Oil we make money off of. So you inject a little bit of water, you produce oil. That's a very economically efficient process. After some time, though, you start producing both water and oil. And as time goes on, it's more water and less oil. Eventually, it's maybe 99% water, 1% oil. We call that the water cut. That's not good, right? If you're injecting water and then on the other side you're producing 99% water, that's not nearly as efficient. The plot I have shown below is a picture of the water saturation versus the distance along that reservoir or rock core. This is not something we've talked about yet. We will in the next coming days. But basically that water saturation is high. It's equal to 1 minus SOR at x is equal to 0. It decreases, and then generally what we have is what we call a shock front, where that water saturation decreases abruptly. But let's not worry ourselves too much with that yet. We're going to explain why we get that either later today or Friday. But more generally, and I think that this is a slide I will show many times, the beginning of each of the next few chapters. And what it says is that the cumulative oil recovery, and we use a dimensionless recovery, NPD, it's the volume of oil recovered, so like barrels or cubic feet, divided by the pore volume of the reservoir, so barrels or cubic feet. So it's dimensionless. That number is going to be greater than 0, less than 1, and it's going to be equal to what I have written on the right-hand side. Now, the thing on the most right-hand side is SOI, which is the initial oil saturation, minus SOR. What that means is that you can't produce more oil than is originally present. So if SOI, the initial oil saturation, is 70%, then you can't produce more than 70% of the pore volume because the remainder is water. But we've also subtracted off SOR. SOR is the residual oil saturation. That's the capillary trapped oil. That is oil that is trapped due to interfacial tensions, and we can't produce that unless we do something unique like inject a surfactant, which is like a soap that reduces the interfacial tension. So in a water flood, you'll never be able to get more NPD than SOI minus SOR. Even if ED, EA, and EI are all 100%, that's the maximum you can recover. Okay, and that's true. You go to very, very long times. You could inject water forever, and that oil will remain trapped, at least in theory. So that is oil that's left behind due to residual or capillary trapped oil. There is also these terms here, which refers to unswept or bypassed oil. Those are things that are due to pore mobility ratio, and they're time dependent. So when a low viscosity fluid like water, or a low mobility fluid, or a high mobility fluid like water, so mobility is the relative permeability divided by the viscosity, displaces something like oil, which maybe has a higher viscosity or at least a lower relative permeability, then you'll get unfavorable displacement, and you'll get what's called viscous fingering. And basically, the water bypasses the oil and finds the producer well, which is no good. Those are all examples of unswept oil, and there's 3 different kinds. There's displacement efficiency, which occurs even in 1D. It also occurs in 2D and 3D, but it occurs even in 1D. And that's what we'll be talking about for the next couple weeks. EA is the aerial displacement efficiency. And a picture of that is down over here, and you can see that you got the swept zone and the unswept zone. So what happens is that the water goes from the injector to the producer, and around the edges you have some unswept oil. Okay, and that changes with time. So these are all time-dependent things. ED, EA, and EI are anyway. Then you have what's called vertical sweep efficiency, or EI, and that is due to the permeability of different layers. And if you've got a high permeability layer, you know, and the extreme case would be like a fracture, but any high permeability layer, then the water is going to zip through that and reach the producer well before the other layers get swept. And we call EA times EI the volumetric sweep efficiency. But again, we're not going to worry about that right now. We're only focusing on 1D, so we'll assume EA and EI are 1 or 100%. It's ED, the displacement efficiency. So when we talk about flow in 1D, we're talking right now just water and oil. We could have gas, but a gaseous phase, but we don't. We might have gas dissolved in the oil, but right now there's no extra phase. So it's two-phase flow. I like to use the term aqueous to describe the water phase, and oleic to describe the liquid hydrocarbon phase. So the oleic phase could include gas that's dissolved in there, but we don't have a third gaseous phase. What we're going to do is we're going to write a material balance. And a material balance is always written in the same way. Whatever goes into some, we call it a control volume, into some volume, minus what goes out is what's accumulated. Right? That's how mass balances work. So any mass in minus mass out is what's accumulated. We can write that mass balance over any control volume. I'll choose an arbitrary control volume, which is the sliver here given by those two black lines. And what goes in minus out is the density of the fluid, it's a mass per unit volume, times the volumetric flow rate, Q, so volume per time, times the incremental time, delta T, over which we do the mass balance. That could be 1 nanosecond, it could be 1,000 years. Okay, we'll talk about what that is, but the mass balance is true over any time interval you choose. You'll notice that I use a subscript W to indicate we're talking about the aqueous or water phase. And I've used a subscript X to indicate that we're flowing in the X direction and we're at this point X right over here. And then this point, which is to the right of it, is some delta X away. That's why I've written that as QW X plus delta X. And that's the in minus out term, right? So you've got mass of water in minus the mass of water out. If they're equal, mass in is equal to mass out, then that's equal to 0, and then we're at steady state. Nothing's changing. But if we're not at steady state, you have some accumulation. So the accumulation is how much mass of water do we have right now at time t versus at some time t plus delta t. And the mass is going to be the volume, delta V, which is really delta X times the cross-sectional area. But that's the bulk volume. The fluid is only in the pore volume, so we multiply by porosity. So that's the pore volume. But we have both oil and water, and we're concerned about water, so we multiply by the saturation of water. So this is the volume of water in the control volume. But we don't want volume, we want mass. So we multiply by the density, which is a mass per unit volume. And I'd like to point out that density, porosity, saturation can all change with time, and they can all change with position. If I divide this equation by the volume times delta T, or area times delta X times delta T, then the equation becomes this. So all I did is divide by A delta X delta T, so over here the delta T's cancel, and we know that flow rate is velocity times area, so Q divided by A is just my velocity U. That's the Darcy velocity, and then divided by delta X. On the right hand side, my A delta X is canceled with delta V, so these go away, but delta T remains in the denominator. Now I mentioned before that delta X and delta T could be any size. They could be really small or really big. We're going to make that control volume very small. We're going to make it so small that we're going to take the limit as delta X goes to 0, and we're going to take the limit as delta T goes to 0. And we recall from our calculus class that when you have these difference equations, as the limit as the denominator goes to 0, we're left with a derivative. Or really, in our case, a partial derivative, because it can be dependent upon both x and t. So we take that limit, we get this partial differential equation. So it's the derivative with respect to x of density times velocity is equal to the derivative with respect to time times density times porosity times saturation. And there is a negative sign over here because we had the value at x minus the value of x plus delta x. So that is a negative sign over there. But this is the water balance. Okay? And it is a material balance just like we wrote up over here. This was algebra, but then we convert it to a differential, a calculus type term. This is the balance for water. You could do exactly the same thing for oil, and you would get this PDE. The reason why it's a partial differential equation instead of an ordinary differential equation, because it depends on more than one variable, x and t. By the way, if we were in 3 dimensions, you'd have an x term, a y term, and a z term, plus the time term. So you have a 4th dimensional PDE. Here it's 2 dimensions, x and t. Okay, so what we really want to do is we want to solve these equations. And solving these equations will tell us things like what is the water saturation as a function of time, which will help us to determine things like the water cut, which I alluded to before. How much water are we producing at the well versus oil? And we'll be able to determine a lot of other things. But we want to know as reservoir engineers, how does the water saturation and the oil saturation vary with space and time? How does the pressure vary with space and time? How does the velocity vary with space and time? And solving these equations is going to get us that. And they are complicated. They're complicated to solve, and in the most general sense, especially when you go to 3 dimensions or 3 phases, but even sometimes in 1D and 2 phases, these equations are impossible to solve analytically, and that's why reservoir engineers often use reservoir simulators. But fortunately, there is a situation where we can solve these equations analytically, and that's the Buckley-Leverett theory. Okay? And it requires some assumptions, some approximations. Some of them tend to be very reasonable approximations. Okay? And what it is a semi-analytical solution in 1D. It's useful for kind of understanding how all this works and doing back-of-the-envelope calculations, but it's also useful for benchmarking or validating numerical solutions. But the assumptions that we include are that we only have 2-phase flow. We have an oleic phase and an aqueous phase. Well, that's not always true, but it's definitely sometimes true. We have lots of reservoirs that don't have any gaseous phase. Another is 1D flow. Well, this one's a little bit more of a stretch. Okay, most reservoirs are 2D or 3-dimensional. But if you line up your wells in a certain way, then a 1D approximation is true. But we do experiments all the time in 1D, and we use it to help us make predictions in 3D. Incompressible fluids. Well, this is an interesting approximation. We spent all of Reservoir 1 learning that oil and water are not incompressible, that they're slightly compressible. So how can we make that assumption there? Well, in Reservoir 1 during primary recovery, it's the compressibility of those fluids that really drove flow. In secondary recovery, the compressibility is negligible compared to the change in water saturation. Water is pushing the oil towards the producer. That's the main mechanism for flow. So while these fluids are not incompressible, they have a very slight compressibility, and for our purposes, we can normally neglect it during water flooding. Another is that there's no capillary pressure. In other words, that the oil pressure is equal to the water pressure. That's not strictly true either, but as I've mentioned before, there are many cases where capillary pressure is small compared to the reservoir pressure. So sometimes that's a good approximation to neglect capillary pressure. Anytime we have a partial differential equation or any differential equation, we need boundary and initial conditions. The initial condition is that the water saturation is some constant value. We'll call it SWI, I standing for initial. And it doesn't have to be, but right now I'll assume it's equal to the irreducible or residual water saturation. Maybe you got there by having a core fully saturated with water, then you injected oil for a very, very long time, and then the remaining water is SWR. You have a constant injection rate at x is equal to 0. So we're injecting water at x is equal to 0. You know, that could be so many barrels per day or so many, milliliters per second. And that's what we would normally do in a reservoir, right? We inject water maybe at a constant rate. And then because the fluids are incompressible, whatever we inject on the left, however many barrels per day we inject, we produce that many barrels of day on the other side. So that rate at x is equal to L is also constant. Now some of that might be water and some of it might be oil, and that might change with time, but the overall total rate is going to remain constant. Okay, so if the fluid and rock are incompressible, like we stated in our assumptions, then density of the fluid and the porosity are going to be constants. They're not going to change with space or time. So we can pull those out of the derivative. So whereas before I had density inside the parentheses and density and porosity inside the parentheses, I don't anymore. And because of that, these densities cancel. So that's the water and oil balance, and that gives me the simpler equation right over here. So the partial derivative of water velocity with respect to space, x, is equal to the porosity times the change in water saturation with time. And likewise, we can write that for the oil balance. If we were to add these two equations together, then what we get is the partial respect to x of UW plus UO is equal to the porosity times the partial respect to time of SW plus SO. But we know that SW plus SO is always 1. Now SW might be changing with time and SO might be changing with time, but if you add them up together, they're always 100% or 1. So that means the change in SW plus SO with respect to time is 0. And if that's true, then UW plus UO, or U, the overall velocity, must be 0. I'm sorry, it must be constant, not 0. It must be constant, right? So if this is equal to 0, the change in U with respect to x must be 0. So that means U is a constant. So that's what I said over there, is that du dx is equal to 0, or U is not a function of x. The velocity, the total velocity, is the same at x is equal to 0, as x is equal to 0.5, as x is equal to 1 at the end of, or x is equal to L. Okay, so now that we've got that, we're going to take our water balance here, this minus du w dx is equal to phi dsw dt, and see what we can do with it. And maybe I'll switch over to some handwritten notes. I think that's kind of where we finished off last time. So I think that's a good place to switch over here. Okay, so what we have is phi dsw dt plus partial mu w dx is equal to 0. This is our water balance for incompressible fluids. And I'm going to recall, this was a problem on your exam, that Fw, the fractional flow of water, is equal to mu W over U, or UW is equal to Fw times U. And we already said on the last slide there that U is a constant. So I can take this and replace it over there. And because u is a constant, I can take it out of the derivative. So now, I'll say therefore, that's what those little 3 dots mean, phi SW dt plus u dFW dx is equal to 0. All I did is replace UW with FWU. I recognized that U was a constant, so I could pull it out of the derivative. And so this is my new form. Okay, so remember SW is the water saturation, FW is the fractional flow, which, by the way, again, part of your exam was that fractional flow is a function of saturation. So these two things are going to be related in some way. We'll get to that in a minute. This is a dimensional form of the equation. All right, and it's dimensional because it's t time and x in terms of like feet, and u is the velocity, v is the porosity. What we're going to do is define some dimensionless variables. We always like to use dimensionless variables and equations. We kind of learned that in our aquifer modeling, and it's because the plots and the solutions are generic, and then they apply to any reservoir. And so we're going to deal with dimensionless variables and solutions. So we're going to define a dimensionless distance, xd is equal to x over L, right? So the length of the the position of the reservoir varies from 0 to L, and so if you divide x divided by L, that means xd is always between 0 and 1. xd will never be greater than 1, not in the reservoir anyway. And then we're going to define another one, which is the dimensionless time. And that's going to be the volume injected, so the volume of fluid, water probably, injected, okay, divided by the pore volume. So that's obviously dimensionless, it's volume divided by volume. The volume injected is the volumetric flow rate, Q, times time. So if I inject 100 barrels per day times 10 days, then that's 1,000 barrels that I injected. The pore volume is the length times the area times the porosity. Length times area is the volume, the bulk volume, multiplied by the porosity, that's pore volume. Another way to write this is Q divided by A is, of course, the velocity, so it's UT over L phi. Okay, so what you can do is you can replace T and X in there, and what you'll get is phi mu L over phi dsw dtd plus u over L dfw dxd is equal to 0. Okay, if you don't quite see how to do that, I recommend you do it yourself. But basically what you do is where you have x, you say x is equal to xdl and plug it into there, and you say t is equal to td L phi divided by mu, and then you pull out the constant variables, and you'll get this equation over here. These porosities obviously cancel. You get a u over L is equal to 0. So another way of writing this is that. Okay. So this is a new PDE. I shouldn't say it's a dimensionless form of the PDE that says the change in water saturation with dimensionless time plus the derivative of fractional flow with respect to distance is equal to 0. Okay, where TD and XD were defined as up over here. This is the dimensionless form. And you know, we're going to try to solve this equation. We're going to try to solve this PDE for water saturation as a function of time and distance. But you know, it still doesn't look quite right because, you know, it's a PDE, it's time and x, but my numerators, I've got a saturation here and a fractional flow there. So I've got two different variables that I'm solving for, and that kind of seems complicated. Fortunately, fractional flow and saturation are related. And so, recall FW is a function of SW. You plotted it on your exam. You're going to plot it on your homework. It's a function of SW. So we can use the chain rule. Use chain rule. You remember the chain rule, right? dy dt is equal to dy dx times dx dt or something. We're going to do that here. So the partial of FW dxd is the partial of FW with respect to saturation, because FW is a function of SW, times dsW dxd. Sometimes I'll leave it like this. Sometimes I'll use a shorthand form. I'll say FW prime dFW dxd. Okay, so FW prime is just the derivative of fractional flow with respect to saturation. Now, on your homework and on the PowerPoint slides in the last chapter, I not only had you make plots of fractional flow versus saturation, but the derivative of fractional flow versus saturation, or FW prime. So now it should be apparent why I asked you to do that. Because we're not just going to be using FW, but we're going to be using FW prime as well. So now I can write the equation as dsW dTd plus FW prime times dsW dxd is equal to 0. That looks a little bit more doable, because now I've only got one variable I'm trying to solve for. What I want is, I'll say want SW is some function of XD and TD. I want to know what the water saturation is in my reservoir at any location XD and any time TD. That would be great. Okay. Right? If you knew that as a reservoir engineer, if you knew what the water saturation was at all locations and at all future times, you could make some really great decisions, right? You could really impress your boss by saying, we're going to go drill a well over here. We're going to do, you know, some sort of stimulation over here. We're going to abandon the reservoir at this time because the water saturation is so high, things like that. So you want the water saturation as a function of space and time. And solving this PDE will give us that. We do need initial conditions and boundary conditions. We had some earlier, and we're basically going to use the same ones, although they might look slightly different. So the initial condition at time is equal to 0, so SW at all locations XD and TD is equal to 0 is equal to SWI. Right? That's some initial water saturation, and that may be equal to SWR. Okay, it probably will in most of the things we do. Then what we have is a boundary condition that says at the inlet FW, all right, FW is equal to 1 at XD is equal to 0 and all times, right? So at the inlet, you're injecting 100% water. So the fractional flow is 1. Now, what you learned is that a fractional flow of 1 doesn't mean that the water saturation is 1. In fact, the fractional flow of water is equal to 1 when SW is equal to 1 minus SOR. Okay, so SW is equal to 1 minus SOR at XD is equal to 0. So that's another way of writing that. So that's our boundary condition. So we got one initial condition and one boundary condition for this PDE. This is a first order derivative of time. So we got one initial condition, a first order derivative of space, so we've got that. And now we're going to have to learn how to solve that. And it's a bit complicated. But let me go back to this equation. We want to solve this. We want to solve this equation. We have this, I'll call it a coefficient, but it's FW prime, which is a function of water saturation. And as a reminder, this was on your exam, it's going to be on your homework, but FW versus SW looks something like this, right? This is 1, that's 0. This is SWR. This is 1 minus SOR. Most of you did quite well on that on the exam. And then the derivative, FW prime versus SW, is the slope of the line tangent to the curve. And you'll notice that this is 0 here, the derivative is 0 there. It's maximum somewhere in between. So at SWR and 1 minus SOR, you'll get something like that. Okay, it'll reach a maximum. Now it's not usually symmetric. My plot kind of looks symmetric, but it's in general not symmetric. But it does equal to 0 over there, and then at the you know, it reaches some sort of maximum. Okay, I'm going to finish today's lecture. I'm going to finish today's lecture with showing you what the solution looks like, and then we'll actually show what the actual equation solutions are next time. So if you were to solve this equation, dsw dtd plus fw prime dfw dxd is equal to 0, to get SW as a function of xd and td, you'll get a plot that looks like this. Water saturation, 0, 1, versus xd, go to 1, okay. And let's just choose some arbitrary time, td1, okay. Well, what happens is that you're not going to be, this is 1 minus SOR. So even at the inlet where you've got 100% water flowing, you do have residual oil present in there. This is, and what normally happens is you'll get something that looks like this. This is SWR. Your water saturation will never go below the residual or irreducible water saturation. But the water saturation is high in the front, it's low in the back. Remember, we've got mostly oil in there at the beginning, okay? It decreases, but then at some saturation, I'm going to call it SWF, I'm going to call this position XDF, there's what's called a shock front. This is called a shock front. It's an abrupt change in saturation. Okay, and this is at one value of TD, we'll call it TD1. Then this is at a different TD, we'll call it TD2. Then at another TD, TD3. So these saturation profiles are changing with time. So this is what a typical saturation versus distance curve looks like at different times. The shape of these curves depend on the mobility ratio, the relative permeability curves, the viscosities, things like that. as we'll soon learn, because the fractional flow and the fractional flow derivatives are dependent upon the mobility ratios and whatnot.